Manolescu. He's going to talk about Floer homology and covering spaces.
Okay, thank you for the invitation to speak. So, yes, I'll talk about the relation between Floer homology and covering spaces. And let me first say that this is joint work with Tye Lidman. So let me start by reviewing the Floer homologies that we'll mention in the talk. So they are associated to a three-manifold Y, a closed, oriented, and oh yes, and we also need a spin C structure on Y. So, yes, so there are different versions of Floer homology. Orschbart and Szabo have the Heegaard Floer homologies, and there are different versions of this. So, I'm gonna, well, the one that contains basically all the information is HF plus. This is a ZU module. But in terms of comparing things, I mean, this is infinite as an abelian group, so it's somehow more convenient to work with finite rank abelian groups, and there are two that are present in the theory. One is HF hat, which kind of is obtained by setting U equals 0 at the chain level, and another is HF red, which is just the torsion part of this as a ZU module. So these two are finite rank abelian groups. I mean, finitely generated abelian groups. Great. So now there is a parallel theory, monopole Floer homology, and well, there are different versions of it. Kronheimer and Mrówka, in their book, they develop the most general version for all three manifolds, and it parallels monopole Floer homology. So, parallels Heegaard Floer homology. So, instead of HF plus, we have a version called HM2, and then instead of HF hat, we have a version called HM tilde. This was actually defined by Bloom, but it's just, again, taking the cone of the U map at the chain level on HM2, and then you can have a reduced version to HM red if you want. Okay, and then there's some theory that I developed a long time ago, the Seiberg-Witten-Floer spectrum. So this is a suspension. This is an S1 equivariant. Oh, I see. Can people see if I let me write it here. SWFYS is an S1 equivariant suspension spectrum in the sense of algebraic topology associated to Y, but just think of it as a space with an S1 action up to stable homotopy. I mean, yes, it's not quite a space because its homology can live in negative dimensions, but it's basically a space up to suspension. Yes, and to this you can associate its equivariant homology or its ordinary homology. There are other homologies as well. Oh yes, and I should say this is just for B1 equals 0. There are other versions of of these constructions. I mean, there's also instanton homology, the original Floer homology for 3 manifolds, and then Seiberg-Witten, from Seiberg-Witten theory, Kim Preishov and Marcoli-Wang also have other constructions. But these are the 3 things that I will mention in the talk, and actually I have to I will use the equivalence between them. So let me state the theorems that say that they are equivalent. So Collin, Gigini, Honda, well, combining their work plus work of Taubes, you get the following theorem, which was also proved by Kutluhan, Lee, and Taubes. And this is the equivalence between the first 2. So HF plus is isomorphic to HM2, and HF hat is isomorphic to HM tilde, and HF red is isomorphic to HM red. Great, so basically there's no difference between that. And then Lidman and myself proved the equivalence between monopole Floer and the homology of the spectrum. So HM2 is isomorphic to the equivariant Borel homology of SWF, and HM tilde is isomorphic to the ordinary homology of SWF. You can define a red version as well, but I mean it's just an algebraic construction from the Borel part, so let me not talk about it. But basically this says that all 3 versions are really the same invariant. Yes?
Is this a graded statement?
It's a graded statement. Oh, I think this one is, well, I don't know. I think this one they didn't quite prove the absolute gradient from the side. Did you?
We didn't, but I think Vini did.
Oh, who?
Vinicius Grip.
Oh, really? Okay. Anyway, great. So that's that, and this one is graded. Yes. Yes. We will not actually use. Yeah, we will not use the grade. We'll just work on the total rank. Great. Okay. So. Okay, so let me mention what are these Floer homologies good for. Well, the typical applications of Floer homology are related to questions of surgery. So Floer homology kind of behaves well with respect to cobordisms, and that's why it can help. Yeah, it can help one to decide, for example, which surgeries on a knot are the same as surgeries on some other knot, like the kind of questions that Duncan mentioned yesterday in his talk, and many others. So surgery is a way of describing all 3 manifolds, but yes, but what I would like to do today is to see if to explain if Floer homology can be related to another very well-known construction in 3 manifolds, namely covering spaces. So, you know, in view of the work of Hegel and Wise, coverings play an important role in 3 manifold topology. But yes, can we relate the 2? So, great. So I'm going to organize the talk basically in 3 parts. So the goals for today. First, I'll explain how to relate Floer homology to coverings. Second, I will specialize to relating L spaces to coverings. See how they behave under covering spaces. And then I want to get to some topological applications. So without reference to Floer homology, once we establish this relation and we also have the connection to surgery questions, we can try to relate covers to surgery and see what we can get from that. Okay, so let's just state the main theorem with regard to 1. So let me call it theorem 1 so I can keep track of them. So yes, make sure I get the hypothesis right. Okay, so with Lidman, so we prove the following: if we have a covering from y tilde to y, and we need some hypothesis, so it's of order p to the n, where p is a prime, when p is prime, and it's regular. And we also assuming that b1 of y tilde equals 0. So we're just going to work with rational homology spheres. This, of course, implies that also b1 of the base is 0. Then we have an inequality between the dimensions of the Floer homologies with Z mod P coefficients. So let's just take, I guess, all of these are reduced when I take SWF is kind of a pointed space. Just to be clear. Yes. So the homology of Seiberg-Witten Floer space with, let's say, of the cover yes, with Z mod P coefficient in some spin C structures pulled back, in some spin C structure pulled back from the base is greater or equal than the dimension of the homology of SWF of Y in the spin C structure S, again with Z mod P coefficient. So as so these are Z mod P vector spaces, and we can take their dimension. And yes, this says that that basically the total dimension of the Floer homology yes, is non-decreasing under coverings, under those assumptions. And, well, so we proved the theorem using the Seiberg-Witten Floer spectrum, but of course, using the equivalences here, we can rephrase it in terms of HM or HF. So let's just do Heegaard Floer. So HF hat of y tilde S Z mod P is greater or equal than the total dimension of HF hat of the base, sorry, phi star of S Z mod P. Great, and we actually have a second theorem. I mean, we also proved it using the SWF, but I don't know how to call, what to call the reduced homology. So anyway, once you translate back into Heegaard Floer, it becomes something about HF red. So there's the similar statement, HF red of the cover is greater or equal than the one of the base. And it has to be done spin C structures by spin C structures, otherwise it's not true. I mean, the base may have more spin C structures than the cover, like S3 over RP3, and then it's, so it's only true in each spin C structure, not overall. Great, so this will be the main focus of the talk. Let me let's see. Let me mention a few other results that came before these theorems, and are proved in a different way, but they're sort of similar in spirit. So maybe the first result of this form is due to Kristen Hendricks from 2011. So she showed that if you have a knot in S3, then the dimension of HFK hat of the knot Floer homology with sigma 2 coefficient is less or equal than the dimension of the knot Floer homology in the double branch cover. So sigma 2k k tilde sigma 2. Right, so instead of taking covers, you can take branch covers, and somehow her techniques only work for 2-to-1 cover, double branch cover, and you can look at the knot inside S3 or inside the branch cover, and you have this rank inequality. So this is the branch cover. Right, and then, I guess also Hendricks proved similar inequality for two periodic knots for H of k hat. So also in knot Floer homology, you can look at a two periodic knot and then at what happens when you divide by the involution, and there's an inequality. Same way, and there's also a result of Lipschitz and Truman right from 2012. So it's something again. This is for 2-to-1 covers, and also for B1 greater than 0. So specifically, you have a map to S1 and the 3-manifold that maps like that surjectively, so pi 1 of y to z, and then you go to sigma 2 using this map, and then this gives you a double branch cover, 2 copies of f here. Let's call this y tilde. So then they show that rank of h of hat y tilde of ys is less or equal than rank of h of hat of y tilde pi star s. Oh, sorry, 2. Twice that, and also they have to assume. Okay, let me just assume that the genus of f is at least 2. It's less or equal than 2. So it's it's a pretty restrictive assumption, but I think maybe nowadays they think they can prove it without the restriction on the genus. There's also this factor of 2, which maybe shouldn't be there, but that's somehow in the same spirit. So our result is just for B1 equals 0, and and the result is just for twofold covers, and in this situation. Yes. You can do it spin C structures by spin C structures, but it's also true overall. Okay, so let me say a little bit. So I'll say a little bit about the proof and the origin of these results, and then I'll go on to applications. Right. So they all come basically. They were inspired by the following theorem due to Smith from 1938. Just a theorem in algebraic topology. If you have an action of a Lie group, of a finite group of order p to the n, and X is compact, so on a compact space, and let Xg be the fixed point set, then The Smith inequality says that the total dimension of the fixed point set with Z mod P coefficients is less or equal than the total dimension of the homology of X with Z mod P coefficients. So this is a classical result. It can be proved using spectral sequences or in other ways. It's kind of the beginning of equivariant homotopy theory. Great. So people then try to do this in Floer homology, and the pioneers here were Seidel and Ivan Smith. Different Smith. In 2010, they proved this inequality for Lagrangian Floer homology. With P to the n is 2, so just for action of Z mod 2, maybe I should say just G equals Z mod 2. And they have some technical assumptions, stable normal trivializations. Of the Lagrangians. Yeah, so you have some symplectic manifold with a G action and some Lagrangians, and the G action preserves the Lagrangians, and you can do a Floer homology in the fixed point set or in the whole space, and they proved that. So yes, so this was for the Seidel-Smith thing. So this was used in Hendrix's results. So she viewed Heegaard Floer homology, I mean not Floer homology, as a Lagrangian Floer homology, and applied Seidel-Smith. Notice, okay, one important thing is that here we talk about covers, so the cover versus the base, whereas here we talk about the space versus its fixed point set. But that's normal. So, well, basically when you have a yes, when you have a Z mod 2 action on some y tilde or y tilde k tilde with a knot, then you get a Z mod 2 action on the Heegaard diagram, say sigma tilde, and Heegaard Floer homology is based on well, on some symmetric product. And if you look at, well, let's say Z mod 2 fixed point set, this contains that sim G of sigma of the base, right? So this is used for y or yk. So yes, so when you have an action, then at the level of symplectic manifold, right, when you have a cover, y tilde goes to y, then you get an action on y tilde, and at the level of the symplectic manifold, what you have for y is basically some component of the fixed point set. So cover and base becomes becomes space and fixed point set. And right, so yes, and the stable normal trivialization, it's this technical condition, but basically what this ends up being is that the Heegaard diagrams have genus 0, which is not usually the case for 3 manifolds, and that's why these results are for knots in S3. For knots in S3, it's okay, right? So this is okay for knots in S3. You can have a bridge diagram, and yes, and that's why it works. But in principle, you should be able to prove similar results for for 3 manifolds and covers in Heegaard Floer homology directly. But right, so otherwise, so if the genus is not 0, then there are basically equivariant transversality issues. I mean, there's some obstruction to achieving equivariant transversality and proving the inequalities. And that's why, I mean, that's why it's hard to prove it to prove this kind of theorems directly in Heegaard Floer homology for 3 manifolds. And the same thing happens if you try to do it in monopole Floer homology. Again, you run into this equivariant transversality issues. So somehow Morse theory is not the kind of the easiest thing to do when you try to do equivariant constructions. So what we did is we used, right, so what did we do is we proved these results using the Seiberg-Witten Floer spectrum. And that's, well, let me say maybe a few words about that. Okay, so great. So proof of theorem 1. Well, sketch. Yeah. So instead of Heegaard Floer homology, we use so theorem 1. Over there, yes, we use the homology of the Seiberg-Witten Floer spectrum. So, right, basically, how is SWF constructed? You look at the Seiberg-Witten map on kernel of the star plus some space of spinors going to itself. So this is something in omega 1 of y, maybe imaginary. So it's some sections or of some bundle over y. These are spinors. So I don't want to get too deep into Seiberg-Witten theory, but okay, let's call this V. So this is an infinite dimensional vector space, and you have this Seiberg-Witten map on it. Yes, and you kind of want to look at the Morse homology associated to the flow of this. So Seiberg-Witten is the gradient of the Chern-Simons-Dirac functional, and you want to do Morse theory in infinite dimensions. But what you do instead is you look at some finite dimensional approximation. So you take larger and larger finite dimensional subspaces of V, and you look at SW lambda from V lambda to itself. You think of it as a vector field. Yes, and basically SWF of y by the way, this is all when B1 equals 0. That's when the construction is done. So this is, what is it? It's, you look at a large set inside V lambda, let's say a large ball, and you look at where the flow comes in and where the flow goes out. And, well, let's call this L as part of the boundary of N. So this is a large open set or closed set inside V lambda. And you look at the exit set, and this is N mod lambda. N mod L. So this is called the Conley index. The homology of N mod L, I mean, it's basically the Morse homology of SW lambda. Well, if it's, I mean, it's a replacement for Morse homology in the sense that you don't have to worry about transversality or the Morse condition, but yes, is the space whose homology is Morse homology assuming transversality, but you can just define it without assuming transversality. Great. So that's so now if you want to look at covers, well, you have y tilde and pi star of s, and you have a g action, so of order p to the n. Then, well, what you notice is that v, so let's say v tilde is the space of sections on y tilde. Well, its fixed point set is exactly v, the space for y, right? So this is for y tilde, and this is for y, right? So this is, yeah, so this is where I'm using that it's a regular cover. So I get, so I have this action of the group, and yes, if you look at, I mean, if you look at, let's say, functions on y tilde, the things that are invariant under G are exactly the ones pulled back from y. So yeah, so the fixed point set is V, and you can look at this Conley index, and what you get is that's basically SWF y tilde S tilde, well, let's say pi star S. The fixed point set is SWF of ys. Okay, I'm lying a little bit. There are some suspensions. Okay, here, let me put it in quotation marks. There are some suspensions. There's some shift in degree that you have to take into account. But since we just care about the total homology, we don't really have to worry about the total dimension of the homology. We don't have to worry about that. Right, so the fixed point, so as a space, the fixed point set associated to the cover, so the fixed point set of the space associated to the cover is the space associated to the base. So then you can just apply the classical Smith inequality. Namely this one over here. So you apply it to the Seiberg-Witten-Floer spaces, and you get theorem 1. So we're using that it's regular in the sense that, so that we have this G action. We're using B1 equals 0 because that's how the construction of the Floer spectrum works. And yes, we're using that it's P to the n sheeted because that's the condition, and with ZMRP coefficients because these are the conditions in the classical Smith inequality.
So those spaces you're applying it to, are they actually compact? Because I think the Smith inequality actually applies in
Yes.
compact type, right?
Yes, they are compact.
But they're actually compact.
Yeah, so n is compact, and yes, and so is L. They have the homotopy type of a finite CW complex.
Right, but I guess I was asking about the distinction between having the homotopy type of a finite.
Oh yes,
Well,
they
Smith
are.
inequality actually applies to things that have the homotopy type of a finite CW complex, not just.
Sorry, I forget in what generality it applies, but they're definitely compact.
Okay.
So yeah. Okay, great. So I think that's all I want to say about the proof. I mean, right. So so what we're going to use in the application is the corollary, the statement in terms of Heegaard Floer homology. So I mean, just to be clear, this proof is not hard. It's like a couple pages, but the other theorems, the equivalences, are really hard. So that's kind of the yes, what will help us get to the applications. Okay, maybe I will leave that on the board. let me leave this corollary on the board as well. So let's talk about L spaces next. Oh yes, part 2. L spaces, yes, so let me remind you, I mean they appeared in some other talks, but so a 3-manifold is called an L space if HF hat of ys is Z for all spin C structures. This implies that it's a rational homology sphere, so that's the only kind of 3 manifolds we will consider. And examples, well, length spaces were the model, that's where the name comes from, just more generally elliptic manifolds, so those covered by S3, double branch covers over alternating links, and large surgeries on L space knots. So once you have a knot whose surgery is one of the previous examples, all the higher surgeries are also L spaces. So this way you can construct many examples. And they're important, so they have some properties. I mean, if Y is an L space, then it has no taut foliations. So that's a standard way of obstructing the existence of taut foliations on 3 manifolds. And I mean, they have application, let's say, no contact structure on Y has a symplectic filling with B plus greater than 0. So it tells you something about fillings of contact manifolds. And it also tells you something about decomposing 4 manifolds. So if you have something like a 4 manifold cut along Y, and both sides are greater than have B plus greater than 0, right, and Y is an L space, then yes, then the Seiberg-Witten invariant of X is 0. So if you have the K3 surface or something like that, you know that you won't be able to cut it along an L space in this way. Yes, so that's some of the reasons we care about L spaces. Now, of course, nowadays people mostly care about L spaces in relation to the following conjecture. Nathan talked about a lot. So conjecture, question, maybe Boyer, Gordon, Watson, maybe plus Juhas. Something is an L space if and only if it has no taut foliation, if and only if pi 1 of Y is not left orderable. So great. Well, yeah, so Nathan checked it for many cases, but it's still not clear if it's true or not. So anyway, let's go back to covers. So I'm interested in how, yes, what's the relation of all these to covers. So notice that, first of all, if Y tilde over Y is a cover, then, well, there are some easy observations. If Y tilde has no taut foliation, then the same is true for Y, for the base. Yeah, so if you had a taut foliation on the base, you could kind of pull it back. That's not too hard to see that you can preserve the tautness condition. And similarly, if Y tilde has pi 1 not left orderable, then the same is true for y. This is even easier because yes, pi 1 of y tilde is a subgroup of pi 1 of y. So if you had a left order on y, you would get one on y tilde. Great. So in view of this, you may ask if the same is true for covers for L spaces. Great. So conjecture, which would be implied by this conjecture, if it's true, if y tilde is an L space, then so is y. Okay, and well, notice this is true for graph manifolds. Because the conjecture is true for graph manifolds by work of Hanselman, Rasmussen, and Watson. So great, but yes, but okay. Now we can do something. We can give a general result. Well, under some assumptions. So we have theorem 1 and L space. Well, basically tells you that the dimension of actually, let's just look at the corollary. So the corollary, if y tilde is an L space, that tells you that this dimension over here is 1. Okay, and well, the Euler characteristic of h of hat is 1 when it's a rational homology sphere. So if this is 1, then this also has to be 1. So let me call this corollary 1. So corollary 1 implies corollary 2, which says that under the same assumption, so regular cover p to the n sheeted for p prime. Okay, well, if y tilde is a Z mod P L space, then so is y. Okay, so unfortunately it's not quite L space, but Z mod P L space. But okay, what is a Z mod P L space? Is the same thing with Z mod P coefficients. So i.e. h of hat of y tilde s Z mod P is Z mod P for all s. So at least for Z mod P L spaces, right? If the cover is that, then so is y. Again, assuming this hypothesis. So, great. Let me make a remark. So Z mod P L spaces may be the same as L spaces. So remark, no torsion has been found in H of hat for B1 equals 0. So people have computed H of hat for various classes of rational homology spheres, and nobody can find any torsion yet. I mean, there might still be some, but so Z mod P L spaces may be the same as L spaces. I mean, in principle, Z mod P L space is weaker than L space. But I don't know. And let's assume, so let's assume we're in the world where, assume there's no torsion in H of hat for B1 equals 0. Let's say this was true in general. Then under this assumption, we could state the following theorem. I mean, well, then that would imply that if y tilde over y is it's a regular cover with automorphism group being solvable, and y tilde is an L space, then y is an L space. So this is just somehow a nice, this is the actual result over here, but you know, it's in terms of Z mod P L spaces. If you forget about the difference, then yes, then you can just look at P to the n theta, then you can combine them and get anything with a solvable automorphism group. And you could say that, yes, as long as it's regular and you have solvable automorphism group, then this conjecture is true. Great. Yes, okay. You could, of course, you get a little bit more. I mean, oh, actually, before I say this, let me also note there exist covers of L spaces that are not L spaces. So it doesn't work the other way. It's definitely like this. So, for example, the Seifert manifold with coefficients -2, 2/3, 2/3, 1/2, 1/2 covers the Seifert manifold with coefficients 2/3, 1/4, 1/4, and yes, this is an L space and this one is not. That's not too hard to find. Yes, but the question is the other way. Our corollary is stronger than the question about L spaces, so you could ask a stronger version of this conjecture, so which I'm less confident that it's true, but it might be true. So open question, if y tilde is a cover, is it true that rank of hf hat ys is less or equal than rank of hf hat of y tilde phi star of s? So you could, okay, so this is, you could drop these assumptions. I mean, we know it's true for, regular covers, but I mean, what if it's irregular, or if the automorphism group is not solvable, or if B1 is not 0? And well, I don't know if it's true or not in general. You could also ask this, I think, how about a degree 1 map? Yes, so Michel Boileau gave a talk about things like this, and yes, you could look at this kind of relations between three manifolds and ask if the rank of hf hat is monotone under this under the existence of such maps. And yeah, this is not known. Okay, great, but yeah, at least we have one result in this direction, so under some assumptions. So in the remaining 10 minutes, let me talk about the relation to surgery. Right, so if we have so let's consider surgery on a knot in S3. So R surgery, I'm not going to define surgery, it was featured in a bunch of other talks. Okay, in S3, so R is some rational number. So hf hat of S3 RK can be expressed in terms of CFK infinity of K and R. So there's something called the knot surgery formula due to Orschwat and Szabo. And yes, and this tells you, I mean, tells you a lot about surgeries on a knot. And now we can combine this with theorem 1. So theorem 1 over there. Yeah, I guess for the corollary. Maybe let me leave the corollary on the board. So theorem 1 plus this gives you constraints on which S3RK can cover some surgery on some other knot. Basically combining, yes, I mean it gives you an inequality, and then from this sometimes you can compute, you can give some formulas for the rank of HF hat and you get a contradiction. So for example, let me give one example. Let's say theorem, theorem 3, I guess. Was there a theorem 2? Okay, great. Okay, so if K, K prime are non-trivial Z mod are L space knots, PP prime, QQ prime greater than 0, and twice the genus of K minus 1, the ceiling of Q over P is less than twice the genus of K prime minus 1, the floor of Q prime over P prime, then there exists no regular cover of order R to the n, where R is a prime. So, I mean, just when you have L space knots, you can compute you can get an actual formula for this, and combining it with the inequality between covers, you would get a contradiction in this range for this kind of coefficients. Let me focus on a result for all knots, but comparing surgeries on the same knot. So okay, so let me first recall the purely cosmetic surgery conjecture due to Cameron, but I'll just focus on purely cosmetic surgeries and knots in S3. So non-trivial knot, and let's say can two surgeries on this be the same 3-manifold? So as oriented 3 manifolds, and R is different from R prime. Then, well, the conjecture says that R equals minus R prime and K is amphichiral. Well, and also, I mean, S3RK, I mean, if it's amphichiral, then this is minus S3 of minus RK, so this should have an orientation reversing, yes, has orientation reversing diffeomorphism. So it's a very special, yeah, so the conjecture, I mean, there has been quite a lot of progress on this, but still a conjecture. It's quite restrictive. In fact, as far as I know, no examples are known of this. So maybe it just never happens, but yes. So let me now ask about virtual cosmetic surgeries. Can this exist? So can you have S3RK over S3R prime K, a non-trivial cover with R different than R prime?
That's R surgery, the conclusion, the second, the last equation, the right hand, yeah, should be R.
Well, they're the
Did you
same.
write a
But yes,
minor?
fine. Okay. Yes, yes. I mean, this, yes. They're both true. Yes. Yes. Okay, so yes, can we have non-trivial covers? So yeah, so let me mention. I mean, for the unknot, you can surely this happens all the time. So notice, like when k is the unknot, then S3 1 over Q on the unknot is S3 is a cover of S3 P prime over Q prime of U, which is LP prime Q prime. And there are examples for all torus knots. It's not hard to see. Again, you can get L spaces, you can get length spaces, and they cover each other. So there's a student of Robert Lipschitz, Keegan Boyle, and he classified when this happens for torus knots, for which surgery coefficients it happens, and he also checked that it does not happen for any other knots with less or equal than 8 crossings. Okay, but it's not known if it happens for hyperbolic knots. So let me state our result. That comes from, again, from theorem 1 and the knot surgery formula. So maybe theorem 4. Yes, K in S3 non-trivial. 0 is less than P over Q less than 1, and the ceiling of Q over P is less than the floor of Q prime over P prime. Then S3, then there is no possible cover between the P over K surgery, P over Q surgery on K and P prime over Q prime surgery on K when this is Rn to 1 and regular cover. So under some conditions on the coefficients, we get a constraint. So let me mention, so for the unknot, this fails. I mean, we're definitely using that this is non-trivial. So if you look at this, this actually would satisfy the assumptions. I mean, you can make the coefficient satisfy the assumptions, and the theorem fails for the unknot. For the torus knots, you have examples of virtual cosmetic surgeries, but the coefficients are greater than 1. So this is for coefficient less than 1. Yes, and maybe, let me just add one more thing. So if from hyperbolic geometry, I think Nathan observed, and it appears in a paper by, it appears in Boyle's paper, an observation that if you fix R, then there are at most 60 possible values of R prime for which this happens, for a specific, for each knot, I guess, it's R and K. But yes, it's still unclear if it happens for any hyperbolic knot, but this gives some constraint. So that's all I had to say.
Are there any questions?
So how do you resolve the case if there's some spin-C structure not covered by this spin-C structure? So you mentioned that there are, so it's possible that a spin-C structure is not covered by.
Sorry. No, I'm just looking at pullbacks. Pullbacks from the base. That's the only thing I'm looking at. Yeah. Yeah.
Can you make an analogous statement for the case B1 positive if you pass a QC question?
Oh, I think this should be possible, but one needs more work. So my student John Fenglin with Sasahira and Kandawit, they defined a spectrum for B1 greater than 0, and but it's kind of corresponds to the Heegaard Floer homology with totally twisted coefficients. So so I think you may expect some inequality like that for that version, but it hasn't been done yet.
Okay, well, if there are no more questions, let's thank Ciprian again. Let's take a 5-minute break.